And in the second part, we will talk about statistical inference. So I remind you that any investigation of public health problem requires several steps. So we take several steps. So first of all, we formulate a question, then we develop a hypothesis. After this, choose and identify study design. This is all preparatory stage when we get ready for investigation. After this, we collect data and present data. And finally, we analyze data and interpret. So statistics as the science which is concerned about collection, interpretation, analysis of data, it helps us in two main aspects. First of all, descriptive statistics deals with enumeration, organization, and graphical representation of data collected from a sample. If we take another part of statistics, which is called inferential, it deals with reaching conclusions from incomplete information, that is generalizing from the specific sample. So, as I said, first of all, we will cover essential questions of descriptive statistics, and after this, we will come to statistical inference. So descriptive statistics is relatively easy to understand because we all sometimes collect data, organize, represent, and usually we deal with a sample, which is a representative part of the studied population. So it is important to understand that there are different types of data. And usually, depending on measurement scale, we have qualitative and quantitative data. This is important because method of analysis, which we will apply for any type of data, will depend on type of data. So the first measurement scale is qualitative, and qualitative data are not measured by numbers. They fall into three categories: binary, ordinal, and nominal. So binary scale of measurement, in other words, is called dichotomous when the possible options for the studied parameter fall into two categories. For example, yes or no. If you have a parameter, smoking status, your parameter can fall into two possible categories: a smoker and non-smoker. That is called binary or dichotomous scale. If you have ordinal scale, it means you can arrange categories and somehow rank them by the certain order, even they are not numerical. For example, if you study severity of pain and you have categories: very severe pain, moderate, mild, or no pain, it means that you arrange your categories from maximum pain level to minimum or no pain. And this is application of ordinal scale for qualitative data. And finally, in qualitative data, you can have nominal scale when the categories are mutually exclusive and they just represent the certain classes of the subjects, for example, ethnic groups or races, or let's say the country from which a person comes, that all are examples of nominal scale. If we have quantitative data, they fall into discrete and continuous. When discrete is similar to categorical because they cannot take any parameter between each number. For example, if you have number of children in the family, it's a quantitative discrete parameter because you have either one child or two or three or five, but it can't be between 2 and 3. If you have continuous data, this is parameter which can fall in any point within the certain range, and most of quantitative parameters like blood glucose level or insulin level or temperature, they are examples of quantitative continuous data. So when we analyze different kinds of data, the most typically what we do about categorical data is constructing of frequency tables. Frequency table is a very simple way to organize data. For example, you have 21 agents of parasitic diseases isolated from children. And if you just write them down, they don't give us any sense. So we will make a summary. We will, first of all, order. For example, here we arrange them according to similarities, and then we make up a table where results are summarized by the type of the parasite, and you have Giardia lamblia, 6 cases, Ascaris lumbricoides, 6 cases, Enterobius vermicularis, 6 cases, and Entanomeba histolytica, 3 cases. So this is a table which summarizes information about intestinal parasites detected in children, in 21 children. So it's usually useful to show the frequency for each category expressed by percentage from the total. So this is called calculation of percentage, and we will take the total for 100%, and we will measure each category as a part of the total, taking 6 dividing by total 21 times 100, and you get percentage. And then when we have distribution, this will be called relative frequencies. Relative frequencies are very good to make comparisons between each other. And usually we analyze this data and we call it analysis of structure or composition. For example, we can analyze structure of mortality by cause or structure of morbidity by age. And in this case, always total will be taken for 100 and each category will be measured as a part from the total. Here is example of summary for categorical data when we studied distribution by the cause of death, and we see that the different classes take different percentage in the total. For example, cardiovascular diseases take 21.96% and oncologic diseases 18.1%. Frequency distribution for quantitative data is also possible to use. For example, age is a quantitative parameter. But if we have distribution of frequencies in students that have smoked at least once, we put in the first column age, like you see, 19, 20, 21, etc. In the second one, we have frequencies. And in the third one we can calculate percentage. So it's an example where we have quantitative data, but we also use measurement by percentage. This example, this slide shows you addition of the last column, which is called cumulative percent, and we use it in order to judge about different frequencies in the total, and it can be quite useful. However, when we have a lot of numerical parameters, it's a bit confusing to make up frequency table, and in this case, we have to make intervals, not just to study every parameter one by one. For example, distribution of frequencies of ages of children with acute streptococcal pharyngotonsillitis, because we have many parameters here, and age of children varies from below 1 to 15. We can combine the intervals of age like below 3, 4 to 6, 7 to 9, 10 to 12, 13 to 15. And then it will be distribution of frequencies of ages in children with acute streptococcal pharyngotonsillitis, but we can see that the largest category is 4 to 6 with parameter 33.5, and it's much better compared to this table where each parameter is a single number. When we group data, it's important to obtain minimum and maximum values and to decide about the number of intervals. Usually, number of intervals is not very large because it's very difficult to analyze parameters if you have so many intervals. Then what is important that interval limits should be estimated and the width should be the same, and we must not have open intervals, otherwise it will be not clear what is distribution of data. So when we present the data, usually you have a lot of parameters, like here, this is a typical statistical data set. When you have a lot of parameters, some of them are numerical, some of them are qualitative, and usually we organize and present data by frequency tables and different kinds of graphs, to which we will come a bit later. In frequency table, we generally can examine our parameters. We can identify distribution, type of distribution. We can see potential outliers, and we usually check for different kinds of errors. For example, we have data examining the number of children in the families, and we have 30 subjects which were studied in the community, and we organize these parameters to the table. So number of children can be from 0 to 8 in this community, and frequencies are calculated for each one, and relative frequencies are also calculated. Then let's say another example. If we analyze age of patients with heart-related problem, we also have age for every subject. Then we make a table, but we put in the table the interval of age, and also we give frequency for each variable, and relative frequency is calculated. Okay, still in many situations when we deal with quantitative data, we will calculate measures of localization, or we call them central trend measures, mean, median, and mode, and we calculate dispersion measures like standard deviation or range. So for any data set, it's very important to determine the heart of distribution, or what we call measures of central tendency. As I have mentioned, there are three: mean, median, mode. So the mean is just arithmetic average when we sum up all parameters and divide by the number of parameters in the sample, and it is called arithmetic average. The median is found by ranking ranking all parameters from the minimum to the maximum, and the middle value is called a median. For example, we have parameters of household income. We arrange these parameters from minimum 6,000 to maximum 50,000, and the one in the middle is 10,000. Will be called a sample median. And mode is calculated as the parameter with the greatest frequency, and we can calculate it in any kind of data, including nominal data. So central tendency is very important because we can find the middle parameters. And usually the central tendency, when we have distribution, for example, in this case, measurement like age 1 to 3, 4 to 6, 7 to 9, 10 to 12, 13 to 15, we can calculate a point middle, which is a parameter in the middle of our interval, and we can make calculation of the mean for a grouped distribution. The central tendency measurement, like median, is dividing distribution into two equal parts, and it's important that the median is calculated in a bit different way if you have odds number or even number. So if you have two central numbers, you just calculate the arithmetic average of these two central parameters, and it will be a median. Well, so the central tendency measures have some properties. For example, the mean is very sensitive to extreme values, or we call them tails, while median and mode are not sensitive. So that is why if you have a small sample, it's not good to choose the mean as the parameter of central tendency. Another important point is that mode can be affected by little changes in the data. So if you have such high variability, it's better to take a median or a mean. Mode and median can be found in a chart. And what is important that if you have symmetrical normal curve, all these three parameters are the same. So median, mean, and mode are equal. So there is a rule which is important when we choose measurement for central tendency. If you have skewed distribution, and we will talk now about it, we will use median, because if you have data which is asymmetrically distributed, it's not correct to take either mean or mode. If you have statistical analysis or inference, we must use arithmetic average, because arithmetic average is the most accurate estimation of the central tendency. Besides this, there are measures of non-central location, which are called quartiles, quintiles, or percentiles. And usually they divide our data set into parts. For example, quartiles divide data set into 4 parts, quintiles into 5 parts, and percentiles in any number of parts which you like. So the next will be measures of distortion or variability. We have several here. The first one is range, number 2 is interquartile range, number 3 is variance, then standard deviation, and coefficient of variation. So range is very simple. It's a difference between minimum and maximum values. And if we have minimum weight in the sample 51.2 and maximum one is 74.2, the range will be 74.2 minus 51.2, which is our dispersion measure. A very convenient way to look at variation is by a graph. For example, you have minimum parameter 12 and maximum parameter 70, and the difference between 70 and 12, which is 58, is your range. Also, it's very important to look at quartiles. The lowest quartile, or we call it 25th percentile, measures the first group, which is from 12 till 30. And 30 in this case is the lower quartile, which means that 25% of observations lie below this parameter. For example, if you have the upper parameters from 57 to 70, this is called, which is 57, yeah, 57 is called the upper quartile or 75th percentile. So the difference between the uppest and lowest quartiles, which is 57 minus 30, this difference is called interquartile range. Interquartile range in this case is equal to 27, and it shows central parameters which lie between the lowest and uppermost quartiles. So percentiles can be used in a large data set when we determine the value below of which a percentage of given data has occurred. The next one is variance. Variance is calculated on the basis of the deviation, what is called x minus x average, or the mean. So this is the sum of deviations over n minus 1. This is called sample variance. If you calculate a variation in the population, we do the same, but we have parameters in the population like x and mu, and this will be our population variance. If you need standard deviation, we will take a square root of this parameter, and it will be standard deviation, which shows how parameters are distributed around the mean. And standard deviation is very good estimation for normally distributed data. Okay, for example, here we have several examples like the mean is equal 7. And here we have also, 1 minute, the mean is equal 7. And you see, because all parameters are equal, standard deviation is 0, which means that variation is extremely low, or you can say there is no variation, all are the same. In the second one, example, sample number 2, the mean is also equal 7, but standard deviation is equal 0.63. And you see, it is obvious because there are some parameters different from the mean. And about the third one, the mean is also 7, but variation is very large, and standard deviation is equal 4.04. So this is example that demonstrates it's not enough to look at average parameter, because the mean is equal 7 for every sample which we take. But standard deviation is 0 in the first example, 0.63, which is very small, and 4.04, which is very large, in a sample number 3. So standard deviation, which is important to analyze, you can understand by standard deviation the type of distribution. For example, if you have low variation or low variability of parameter, your data set will have in graph the form of this picture, picture number 1. So you see that the distance between average and extreme values is very low. If you have large standard deviation, we will have the distribution which is spread out over a range of values, and this is the case of high variation. So 3 types of distribution which we usually have are called negatively skewed distribution, positively skewed distribution, and symmetric distribution. So if you have symmetric distribution, we have absolutely symmetrical curve which looks very smooth, and the mean, median, and mode are equal. If you have distribution which is skewed to the left, we call it negatively skewed. In this case, the maximum parameter of central tendency is mode, and the mode will be more than the median, while the median will be more than the mean. If you have a positively skewed data or skewed to the right, you have maximum parameter of central tendency, the mean, and the mean is more than median, while the median is more than the mode. So usually if you have skewed distribution, the choice should be made in favor of median, because both mean and mode are not accurate estimates of central tendency. Okay, so here you see that there is a relationship between the mean, median, and mode, and we should be very careful when we choose parameter of central tendency. Besides the parameter of central tendency, it's important to judge about distribution when we identify either it is unimodal, bimodal, or multimodal. In most of cases, you have unimodal distribution with only one central tendency. If you have two central tendencies, it's called bimodal. For example, distribution of height in men and women, it has bimodal distribution because average in women is lower than average in men. If you have, for example, a study on blood pressure and there are subjects who are normotensive and hypertensive, you will have also bimodal distribution. And if you have multimodal distribution, there are several tendencies, and in multimodal distribution, there will be like three humps, versus two humps in bimodal and one hump in unimodal. So there is a very important empirical rule which says that 68% of measurements fall within one standard deviation around the mean, 95% of measurements fall within two standard deviations around the mean, and 99.7% of measurements fall within three standard deviations around the mean. Well, this rule is very important because we can use it for making some generalizations on the basis of knowledge about distribution. So we can draw up a picture where the beige color is 68% of data within one deviation. The blue color shows 95% of data within two standard deviations, and green color shows three standard deviations, which is 99.7% of data. Example, suppose we know that the reaction time of a particular drug has a normal distribution with a mean of 10 minutes and a standard deviation equal 2 minutes. So we can use empirical rule and draw a conclusion that 68% of subjects who take the drug will have reaction time between 8 and 12, because this is the interval of one standard deviation, the mean 10 plus minus 2. 95% of the subjects who take the drug will have reaction time between 6 and 14 minutes, which is within two deviations, or 10 plus minus 4. We get 6 and we get 14. And finally, 99.7% of subjects who take a drug will have a reaction time between 4 and 16, which is within 3 deviations, and obviously it's very large range. Okay, how can we present the data? The easiest way to present categorical data is by a bar chart, when every bar represents the data amount for each group. And usually a bar graph is very clear, it's very simple, and it is used to show each particular category. It's important to remember that must have a title, scale, labels, and proper illustration. For example, here you have a bar chart where time spent sedentary in leisure time by age and gender is given according to the results of health survey. And we have a bar chart where the categories are gender groups, men and women, and also they give comparison for each age category. So this is the case when a bar chart is really very helpful, and we understand that in both weekdays and weekends, the young people have less sedentary time, compared to older people. Well, though the most active people are actually middle age group from age 25 to, let's say, 54. The stacked bar chart is used when we have a lot of specific parameters within one bar. For example, voluntary male medical circumcisions. We show that they are rising from year to year, and we compare 15 countries for the last 10 years. And you see each color shows the country, and this is called a stacked bar chart. It is quite convenient because we show really a large data set by these descriptive statistics. If you have categorical data and you show percentage, the Basel graph. In this case, every sector corresponds to the category, and we will use each category colored differently to demonstrate its amount. So the same as in a bar chart, we must remember about title, legend, and all important markers. For example, global causes of child death, and we have many categories of the causes which are colored differently. And we can see that a lot of 41% of deaths are neonatal, and neonatal deaths contribute a lot to the global children deaths. This one is called a line diagram when we have the axis X or horizontal with the time scale, and axis Y shows either rate or absolute number. So the best way to have analysis of time trend is this kind of graph. Yeah, for example, you can see that HIV grows in Russia. The line graphs are used here to make comparison between categories of fast food, and we see that in Australian teenagers, they have increased consumption of pizza and hamburgers, but decreased consumption of fish and chips. Okay, line diagrams are good to show trends over time. They can be short-term for a short period. They can be long-term, which we call secular, and they can be irregular or cyclic, but repeating the same trend. And if they are absolutely irregular, it's called fluctuation. And line diagrams are good to study prognosis, which means when we want to look in the future using the data set for the previous years, we can make a good prognosis for the future time trend. Histogram is a kind of graph which is good to study frequency distribution, and we will have some parameter on this horizontal axis and frequency on vertical one. What is important that in a bar graph you have the spaces between charts, while in histogram you have no, because the important thing for us is the area under the curve, under the histogram. In a bar chart, we pay attention to the height of the bar, to the length of the bar, not to the area of the bar. If you use frequency polygon, it's the way to look at distribution. So we just connect the plots of the frequencies, and it will be called frequency polygon. Frequency polygon can be used also for comparison. For example, we study serum cholesterol in males aged 25 to 34 and 55 to 64. And we see that frequency polygons are different, and the one for the older people, it shifts to the higher parameters of serum cholesterol level. The next type of graph, it's called a stem and leaf plot, and in this type of graph we have a data set when we list the 10 digits in a column from the minimum to maximum. It's called stem. Then we make a vertical line, and for each number in the set, we write 10 digits. For example, 56, 5 is stem, 6 is a leaf. 70, 7 is a stem, 0 is a leaf. So we do like this for every parameter, and we show also our data by frequency distribution. This one is a kind of graph also used for frequency distribution. It is called box and whiskey plot. In this graph, we have minimum value in data, maximum value in data. Then we have percentiles, which we have discussed, upper and lower. And the box is formed by 25th and 75th percentile. The line which divides the box into two parts is called a median. And generally, this graph is very good because you see a lot of information from one picture. The potential outliers are shown by the dots, and they are lying out of 3 standard deviations. For example, here, results of the serum folic acid in patients with Alzheimer's disease and with other kinds of dementia from the Mediterranean. And you see that folic acid concentration varies a lot in people with Alzheimer's disease, vascular dementia, or mixed dementia. That can be used for screening of the people or for putting diagnosis. But what is important that in vascular dementia, the folic acid is low and variation is also very low. In Alzheimer's patients, variation is very high. Or let's say here, leukocytes count in different days after surgery. And also you can see outliers are a lot for day number 3 and day number 7. And this is a box and whiskey plot that shows very high range. So minimum variation is on day number 3. For example, this is distribution of diastolic blood pressure. Also, we have minimum, maximum parameters, quartiles, and median. This is a dot plot, which is a very good graph just to show distribution, like results of average academic performance for girls and boys are compared. Or dot plot when we have just 2 parameters compared, like for younger people and age under 25 and people 35 plus, and we study prevalence of hepatitis C viral infection among people who inject the drugs. This is example of the whiskey plot, and we have the recorded alcohol consumption among adults in 2 different years, 2000 and 2015. So this is a kind of graph which is very good for dichotomous data. Dichotomy means 2 parameters only, and you see that for some countries like Lithuania, the range is very high, while for others it's very low, for example in New Zealand. Okay, so this is basically about descriptive statistics, and let's say after a short break about, let's say we will have until 3:50. Okay, and then we will continue with statistical inference. Так, okay, so let's continue. So the second part of our lecture will be devoted to statistical inference and testing of hypotheses. Well, inference means, first of all, when we use a random sample to learn something about a larger population. And it is crucially important to understand that if you study just a group of subjects and we analyze the data in a particular sample, this is descriptive statistics. If we want to generalize our conclusions and apply conclusions from the certain sample to the whole population, we need to use statistical inference. So there are two ways to make inference. First of all, to estimate parameters, and the second one to test hypotheses. When we estimate parameters, we either estimate the average or proportion or value of rate, and we make estimation of intervals within which our parameter can fall. When we test hypothesis, we check some concept that we apply and we usually observe in the sample. So when we check it for the whole population, we make hypothesis testing. Some important definitions. If you have a sample, we use the mean, we use standard deviation, and we use proportion or estimates. If we have a population, we will use estimates which are written by the Greek letter mu. Our estimate of standard deviation will be sigma, and estimate of proportion will be p, the Greek letter. So how can we make estimation of parameters? For example, we have a population. From this population, we take a sample and we estimate an average, let's say the mean, in the sample. So our mean parameter is equal 50. So this is called point estimate, which is exactly measured in the studied sample. If you want to have interval estimate, you will detect the certain range of parameters and you want to be 95% confident that population average or population mean lies between some given interval. In this case, it will be, let's say, between 40 and 60. That is the idea of interval estimate. So usually when we make statistical inference, we have a parameter which is measured by statistics plus and minus our error, or we call it standard error. So in standard error, we make estimation of the variation in the population, and we add to the statistical parameter this error. So the sampling distribution is a crucial term which we use in statistical inference. For example, you can see here different samples. So there are 3 different samples. And in every sample, we can estimate our parameter. For example, if you measure average blood pressure, in 3 different samples, it will be measure of X, okay, or the mean in the sample. In sample 1, it will be X1, in sample 2, X2, in sample 3, Xn. If you summarize these parameters from many samples, you will get sampling distribution, which is distribution of a statistic across an infinite number of samples. You must understand that we can take samples as many as possible. You can take 2 samples, 5, 10, 20, but it can be as many as possible. If you measure P, for example, you measure how many people have positive test for HIV, and you measure it by a proportion or rate, that will be p-value. And you do absolutely the same. You measure p-value, rate or proportion in sample 1, in sample 2, in sample 3, in sample n. Then we put these parameters in our graph, and you will still get sampling distribution. So the idea of the standard error is to calculate this difference or sampling variation for the mean or for the proportion. So if you have a quantitative variable, it will be standard error of the mean. If you have a qualitative variable, you will calculate standard error of the proportion. Those are the formulas. Standard error of the mean is calculated as standard deviation in the sample divided by square root of n if n is more than 30. If you have a small sample when n is less than 30, we change the formula by n minus 1. If you have to calculate a standard error of the proportion, so meaning you analyze a qualitative parameter, the formula is p times 1 minus p over n, and you take a square root of this ratio. Obviously, P is proportion. For example, you have 3% of people with HIV positive test. So P as a proportion will be 0.03. And 1 minus 0.003 is your result. If you measure it by percentage, like 3%, instead of 1, you will write 100, and you will write 3 times 100 minus 3 divided by number of subjects. So we estimate confidence interval or the range of parameters within 95% of samples lie by this very simple picture. We put here alpha. Alpha is a parameter of your possible error, and you have the central parameter mu and standard error in both parts, to the right and to the left of the mu. So the idea of confidence interval is to estimate the range of parameter within which 95% of samples lie. So you will have estimation of x average minus 1.96 times standard error, and the mean plus 1.96 times standard error. And this we can easily calculate and measure confidence interval, which is also called uncertainty level. So if you have very large confidence interval, it means uncertainty level is high. If you have very narrow confidence interval, it means you are quite certain about estimation of the parameter, and it shows an accurate estimation of population parameter. So when we have P or proportion, yeah, just instead of X in z-axis, we will write P, and the idea is exactly the same. We will write P minus 1.96 times standard error and P plus 1.96 times standard error, and this range will give us confidence interval for estimation of the proportion. How can we interpret confidence interval? There are two ways to interpret it. The first one is called probabilistic, or it's like in statistical science where we use the laws of probability. Interpretation of confidence interval is that in repeated sampling, the certain percentage of all intervals around the sample means will be in the long run, including population average. I would say that in public health, we use practical interpretation of confidence interval when we say that we are confident that the single computed confidence interval contains our population mean. And this is really much better, I think, and easier to understand, because in reality, we have often estimation of confidence interval, and we understand that within it, there is a population average. Okay, just in order to understand better, we will discuss some examples. Like we have a study where epidemiologists studies the systolic blood pressure in a random sample of 100 hypertensive patients. The mean was 170 with a standard deviation equal 10. So this is example of a large sample because sample size is more than 30. Okay, what we will do, our population mean, which is called mu, is our sampling mean plus minus parameter z times standard error. So we will calculate confidence interval as 170, which is the average, plus minus z. Z is fixed. It is always equal 1.96 for a large sample times a standard error. So standard error is 1, so our confidence interval is equal 168 to 171.9. This is the calculation of confidence interval for the level 95%, which is the most typical way to calculate standard error. If we have another example for the proportion, for example, a survey of 140 people with bronchial asthma finds that 35% of people had allergy to the house dust. So we construct the 95% confidence interval for population proportion. How will we do it? We must calculate standard error. Standard error formula will be our parameter, 35%. So 35% of proportion is 0.35. So in formula, we use 0.35 times 1 minus 0.35 divided by number of subjects in the sample, which is 140. So our standard error is 0.04. And now we can use this standard error for calculation of confidence interval. Confidence interval is calculated as proportion 0.35 minus z, which is 1.96 times standard error, and 0.35 plus 1.96 times 0.04. So we will get the 95% confidence interval from 27 to 43, which means that population proportion, percentage of people who have allergy to dust, not in our sample, but in the population of people with bronchial asthma, it will vary from 27 to 43. Okay, so you see here the range of parameters is not so large, and that is why it is valuable. If we get that 35% of people with bronchial asthma have allergic reaction to the house dust, and confidence interval is from 5 to 95, it is absolutely meaningless, and we cannot use it for any reasoning. Okay, now we come to hypothesis testing. Hypothesis testing is a statistical method that uses sample data to evaluate a hypothesis about the population parameter. So hypothesis testing, it enables a researcher to differentiate between real pattern and random pattern in the data. And we can check by this method either our idea is wrong or maybe it is true. And what we call statistical significance, it means that we can repeat our findings and we will find the same results again and again if our hypothesis is true. If our hypothesis is wrong and hypothesis testing shows that it is wrong, it means that our pattern in the data is different from what we expect. And then we must reject this hypothesis. Okay, first of all, we should start with definition, yeah? What is a hypothesis? So hypothesis is an assumption about population parameter. So you understand that we don't know population parameter because population means everybody in a studied group. But usually we have a sample, a group of subjects which we study. So we assume that the mean systolic blood pressure of participants is 120 millimeters Hg. Okay, so then we must formulate null and alternative hypothesis. What is called null? In null hypothesis, we say that there is no difference between studied groups. And usually in null hypothesis, we say that two compared groups have absolutely the same parameters. And if there is a difference, it's just due to chance. So in our case, null hypothesis states assumption that systolic blood pressure of participants is 120. Alternative hypothesis is opposite. For example, in our case, we say that systolic blood pressure of participants is not equal 120. And actually, we don't know. Either it is below this parameter or maybe it is above. Well, so then we decide about level of significance, which is called alpha. And level of significance defines unlikely values of the sample statistic if null hypothesis is true. And we also call it rejection area of the sampling distribution. In medical studies, the level of significance should be 0.05. It is maximum. And it can be even less, like 0.01. Usually the level of significance is selected in the beginning by the researcher, and it provides critical values of the test. So they will be different for 001 and different for 005. And if you draw these levels of significance on a graph, you will see that alpha will be on the tails on the right and on the left tails, which we call rejection levels. And by the yellow stars, we show critical values. So usually in any statistical test, we calculate these critical values. And if our parameter is not satisfied to the hypothesis, which means rejection area is not covered here by our parameter, then we have to reject our null hypothesis. Okay, for example, here you have just interpretation. You have interpretation of the result possibilities. So we have true result, like in the 2x2 table, and error or false result. So type 1 and type 2 errors, we call them alpha and beta. So alpha error is called false positive, while beta error is called false negative. And usually if you have false positive error or type 1 error, we prove actually hypothesis which is wrong. So in type 1 error, the situation is that we formulate wrong hypothesis, but just by chance we reject the null hypothesis and we take research hypothesis not correctly for true. In type 2 error, situation is opposite. The null hypothesis is false, but we fail to reject it. So that is why we just by a mistake or by the error, we are not able to reject the null hypothesis. What are the factors? The factors which influence the errors are, first of all, related to sample size. You see, sample size or n, it is very important. So type 2 error will increase if your sample size decreases. So to avoid type 2 error, it is important to have a large sample size. The next thing is about a true value of population parameter. Type 2 error increases when the difference between hypothesized parameter and true value decreases. And opposite, if you have the true value of population parameter, it will determine our type 2 error in terms of reduction when difference between hypothesis parameter and true value increases. The next one is a significance level. Alpha or significance level determines type 2 error and it increases when alpha decreases. So they are vice versa, yeah? And about standard deviation, or in other words, variability or variation. So type 2 error increases when you have more variation. If you have low variation, your type 2 error will be less. Okay, p-value test is important. Sorry. So probability of the test statistic will depend on our critical values. So what is important that if p-value, if p-value is less than alpha, we reject null hypothesis. If p-value is more than alpha, we accept null hypothesis. Okay, example. Yeah, in our case, we said about true result of the mean in systolic blood pressure. So we formulate null hypothesis, mu is equal 120. We formulate our research hypothesis. We choose alpha 005, we choose n, and then the test. And then what we do in hypothesis testing, we calculate test statistic, but actually what we are interested in is just p-value. So that is why when we use computer software, it's very easy, yeah, but you pay attention to p-value, how much it is, and if it is large enough, we can reject null hypothesis. We search for critical value, we make statistical decision rule, and finally make a decision. If we have one sample mean test, the main assumption, which is important, that population is normally distributed, and we make the statistic. For example, the normal body temperature, yeah, we ask, is it actually 37.6 degrees Celsius? And we state null hypothesis that population average is 37.6, while alternative hypothesis that population mean is not 37.6. Then we make a data set. So we take 18 people who have normal body temperature. So we measure body temperature and summarize data with a test statistic. So these parameters are all given below. So 18 subjects, the mean is 37.22, standard deviation is 0.68, standard error is 0.161, and our t is 2.38, which is calculated according to the number of subjects. So p-value in this case is 0.029. Okay, then we look, you see, because n is 18, degrees of freedom is n minus 1, so it will be 17. For p-value 0.005, critical value is 2.110. 2.110 should be our critical parameter. Okay, what is about our situation? Yeah, we have degrees of freedom, we have p-value, and we can put it on the graph. So critical values, area to the left is minus 2.11, and to the right 2.11, and our t, which is taken from the formula, is 2.38. Okay, 2.38 is here, which means in the area of rejection. So the value of 2.38 in the table, it shows area of rejection. So we have to decide, So our conclusion will be that the mean temperature in the human population is not equal 37.6 because our area, our parameter t, it lies in the area of rejection of a hypothesis. So we use alpha 0.005, and we understand that in this case we are not able to say that our hypothesis was correct. Okay, one sample test for the proportion. It involves categorical variables. It requires either fraction or percentage of population in a category. We will use sample proportion, and we will use z-test. So z-test is computed, and P will be a proportion in the population according to our hypothesis testing. So critical value, just remember, for 5% P, it is 1.96. For 0.01 or 1% P is 2.58. Okay, we have a study about diabetic patients in a large city. So 100 of people with diabetes out of 400 have diabetic foot. So we conclude that 20% of patients with diabetes in the sampled population have diabetic foot. We have to test this hypothesis with alpha level 5% or 0.05. How will we do it? We will take the formula, calculation of Z. So the difference between our parameters in our case is 20%. So we calculate Z, which will be equal 2.5. 2.5 is more than critical value of 1.96. So you see, it will lie again to the right from a critical value of positive 1.6. So we have sufficient evidence to reject the null hypothesis of a value 20%. So we conclude that in the population of diabetic, the proportion of people who have diabetic foot is not equal 20%. So we have to reject the hypothesis. Okay, here you pay attention. We have standard error. So standard error is calculated as 0.2, which is our proportion, times 1 minus 0.2 divided by 400, which is a sample size. So the difference in studied groups, we consider 5% is enough. So that is why we use 25 minus 20 over standard error. Okay, what else can be done in statistical inference? Obviously, we can make comparison of means. And this is what we usually do. Like we compare the result of treatment in group 1 and group 2. So we can calculate, for example, cholesterol level in patients of group 1 and cholesterol level in patients of group 2. So then our hypothesis will involve comparison of means. And then the data can be obtained either from paired or not paired samples. The paired samples means matched, let's say cases and controls, if you have case control study. In many cases, we have not paired data, not paired samples, which we call independent samples. Okay, how to obtain paired data? Paired samples occur when the first measure is matched with the second measure in the same subject. Like you remember, we discussed crossover study. In crossover studies, we usually have paired data. For quantitative data, it usually occurs when we have repeated measurements on the same person. For example, patient first got treatment A, and we measure blood pressure, then treatment B, and we measure again blood pressure in the same person. So it will be paired data. Let's say in a study to determine whether birth weight measurements are adequate, we compare the birth weight of newborns from a hospital. So measurements were performed by different people to control measurement bias, being observer blinded to the measurement of another observer. If we have non-paired data, they are independent, which I have said already. Okay, for example, we study effects of a new drug to treat parasitic burden of Ascaris lumbricoides, and patients are randomized to receive treatment A or treatment B. So effect of the drug in each group will be measured and compared. So in the analysis of paired data, we calculate the difference between first and second measurements. This gives us sample of differences, and then we apply methods of analysis for quantitative data from one mean. Well, if we have paired data, like here, we will analyze observer 1, observer 2, and the difference, like two measurements in the same subject. For example, one observer measured a baby and another one, and you see this is the difference, and the differences are summed up. And in quantitative paired data, we calculate the mean of differences, standard deviation, and then we can make analysis of the confidence interval, which is calculated. If we have a confidence interval at 95% level, it tells us that we can be quite confident that the true mean of the differences in the population is between the confidence interval to the size of the mean of the differences of the sample. Okay, so we use exactly the same formula with our parameter of sigma plus minus 1.96 times standard error. I remind you that here we have standard error of the mean, yeah? Okay, so we calculate confidence interval, deviations is minus 34, then we have standard error 44.6, and this is confidence interval from minus 21 to 53, which is very high. But you should understand that this is the difference between subjects. So the difference between measurements that were made by different observers, it varies from minus 21 to 53 grams, yeah, because we measure birth weight by grams. So confidence interval, which in this case 90%, is from minus 107 to 39. Okay, a hypothesis test for a mean of the differences gives us, first of all, a confidence interval, which will be 95% range to the sides of the mean of the differences, that we have confidence in 95% of times, including this difference. So then we calculate probability that there is no difference between the paired observations in the population. And then we will formulate null hypothesis, which is equivalent to say that distribution of the mean of differences in the sample is normal. And standard error that depends on the standard deviation of the difference in the population. So we will test a hypothesis, calculating z-test, and we will calculate value of z in order to decide either to reject or accept null hypothesis. For example, we have seen that the average difference in the weight in 10 babies was minus 34, with standard deviation 140.9 and confidence interval at 95% level minus 21.42 to 53.42 grams. So we want to find if the measurements taken by two observers were really different, or maybe this difference is just due to chance. So we say that null hypothesis is all possible measurements taken by two observers are equal, or the mean of the differences in the population is zero. So alternative hypothesis says that the mean of the differences in population is not zero. And then to test hypothesis, we calculate z. So z will be minus 34 minus 0, over 44.6, and we get the z. So again, we have to look in the table. So minus 0.76, you have to understand where it lies. So we refer to this parameter. So in the table, and we check that p-value is equal to 0.44. It's extremely large because 0.44 is much more than 0.05. So we say that null hypothesis is true. So there is really no difference. And this sampling variation is just by chance because our p-value is too large. So we cannot reject null hypothesis. Well, how to obtain p-values? We use either tables, which are given in the textbooks of biostatistics, or we search for that value obtained for the test in the columns. The small paired samples, when the sample size is small, distribution of samples is not exactly normal. We use t-distribution, and usually it's a small data set. So we use the values of t-distribution for calculating confidence interval and test hypothesis. Okay, so here we have exactly the same principles, just we use not z, but we use t, and our estimation of the interval will be parameter plus minus t times standard error. So we will calculate difference between parameters and then divide by standard error of the difference. So we use also degrees of freedom to find how much is our statistical critical value. And let's say example, we ask, do smokers have a different blood pressure from non-smokers? So in a sample of smokers, systolic blood pressure was 138, while in smokers 148. So the difference is 148 minus 138 is equal 10. So then we must calculate standard deviations for both of these groups, and then we find parameter of t, because we used here t-test. Okay, we will use sampling distribution. And in sampling distribution, we have some rules like there must be normal distribution, or the shape of distribution becomes closer to normal when it is large sample, and we follow some principles between, for example, the difference between two means and standard error between two means. We must calculate them and then find the difference between them by ratio. Okay, so this will be the formula, which is combining two errors. So two standard errors. Standard error 1, it is here, sigma 1 over n1, and standard error 2, which is sigma 2 over sample size 2. And this formula combined for standard error of the difference will use square root and the sum of this raised in power of 2. Okay, so in practical classes, we practice this. For example, in our practical task, if you have a study to evaluate efficacy of oral rehydration solution in children with acute diarrhea, 40 children in a treatment group, 40 children in a control group, we measure duration in hours of diarrhea and standard deviation. So you see, standard size is 40, duration in treatment group 72, in control 120, standard deviation is 10 and 12 respectively. So we will calculate confidence interval, 95% for the difference between means. So we calculate the difference first. The mean 1 minus mean 2 is minus 48. Then standard error, it's 2.47. And then we calculate our confidence interval of the difference is given here. Well, so the difference is minus 48 hours with standard error 2.47. So we conclude that in a population, the difference between mean duration of diarrhea will be from minus 52.8 to minus 43.16. So the interval doesn't include the unit, so we can say that the difference of means is statistically significant. So hypothesis testing for two independent means will also require calculation of probabilities. We use that test, so principle is exactly the same. For example, we have to estimate about efficacy of use of oral rehydration therapy. So we will have to calculate p-value. And if we find that p-value is very low, like here, it is 0.0001, so we say that the difference is not due to chance or it is statistically significant. Okay, when we have small samples with two independent groups, procedure is again the similar, but just calculation of standard error will have correction n-1. It's just a correction which we use for small samples. Okay, for example, study of treatment of iron deficiency anemia when we compare students in a village school who either receive treatment or do not receive. So we measure levels of hemoglobin. After 3 months of therapy, we will compare. So in the first group, 15 subjects, iron level 14.8, and this is standard error 0.5. In iron B, 13, 12.1, and 1.1. So we will calculate confidence interval, then we calculate our variation, and you see our standard error will be 0.32, while confidence interval is from 2.04 to 3.36. And we say that our t is 4.44, 8.44, which is very large. So it means that there is a difference between groups because t is more than 3, more than critical value. So basically, yeah, that's all because just our time is finished. But I can say that in the class, yeah, we will discuss all these examples, and really we need to practice these questions because when you just listen, it's very difficult to get the true idea. Yeah, so the idea is to make comparisons between the studied parameters and to use the proper statistical test to check the hypothesis. So we will do it in practical classes when we discuss this topic. Okay, so today it's time to finish our lecture. Okay, so next time we will start talking about public health practice, and we will talk about family planning, medical demography, and preventive medicine. And by today's lecture, we finish talking about methodology of the subject, by statistics and epidemiology. Okay, I remind you that the link to the lecture will be given in the Moodle site, okay? And it will be available, I think, for 2 or 3 days. For people who are not able to listen to the lecture in these hours, you can do it another time, which is maybe better for you. Так, все, до свидания.
До свидания.
До свидания.
До свидания.